Hello guys, good afternoon. So last class we started with the nomenclature and naming of the compounds. And I show you the most common ions using, particularly in the cations, we saw the monoatomic cations, and we saw particularly those just using one. But the problem I told you occurs here with the transition methyls. Because in the transition methyls you can have multiple values depending on the cases, and here are the most common ones, and you need to be familiarized with that. Okay, so in this case we have chromium. For chromium we have +2 +3, and we place the naming in parentheses, just the balance, in this case 2 or 3. Yes. So chromium 2, chromium 3. In the old nomenclature, okay, we call them like O's and ik. So O's for the lower balance and ik for the higher balance. But in the systematic, which is the one we use nowadays and accepted by UPAC, is this one, in parentheses Romans 2 and 3. Lower oxidation and higher oxidation number. So this thing happens for cobalt, this thing happens for copper, iron, lead, and so far. So in this way, it's even easier than just remember these suffixes that we used to employ a long time ago. When I studied my first time college, we used the old one in that case. Nowadays we use this one, which is more simple. So here is just a combination. I will skip this simple, just combine the cations with the anions we learned from before, tin fluoride, chromium iodide, ferric oxide, and cobalt sulfide. Just remember the charges. So in the case of tin, we have tin +2, fluoride is -1, so the formula is SnF2. In the second case, we have chromium, and in this case, this 3 is coming from chromium 3. So in this case, we have an iodide from chromium. We have chromium 3 iodide. In the case of ferric is a common name, so sometimes you will find the common names also very frequently. And the last is cobalt. The anion is sulfide. The compound is cobalt 2 sulfide. In this case, we skip the 2's because you can cancel the 2 with the 2 of the subindexes. So remember, sulfide works all the time with -2 because of the position of the sulfur on the periodic table. It's far away 2 electrons in this case. So the big problem for many people is this, the one with the polyatomic ions. So you need to, there's no way, you need to memorize those names. You need to be familiarized with them. So you need to practice and memorize these common names. Okay, of course they are not all here, but here are the most important ones. But particularly I will refer to the ones that can be formed with 3 halogens, different from fluorine. Chlorine, bromine, and iodine. In these 3 cases, we have the stream cases. And in those cases, we can have 4 different denominations that use prefixes and suffixes depending on the state of oxidation of the halogen in that case. So here you can see that for the chlorine, we have hypochlorite, chloride, chlorate, and we have even one more, which is the perchlorate. So let me show you what happened on those cases. Particularly the halogens are the special cases. So we have 4 different namings. In this case, we have hypoite, we have ite, we have ate as a suffix, and finally we have a prefix, which is per, and finally ate. So those names are coming from the different oxidation states from the chlorine. And you will say, well, Dr. Lopez told me that elements from group number 7, they tend to work with -1 because they are close to. But they work with -1 when they are attached to elements which are less electronegative than them. But when they are attached to elements which are more electronegative than them, okay, they work with positive balance. And those balances can be +1, +3, +5, and +7. And depending on those balances, you have the different names. So let me show you what happened. You see that from the whole halogens, you don't include fluorine. And the reason why not fluorine is because fluorine only works with -1. It cannot be positive because fluorine is more electronegative than oxygen. That doesn't happen with the remaining chlorine, bromine, and iodine. So in this case, again, the oxidation numbers we will consider is +1, +3, +5, and +7. Now, let me show you what and how to calculate the oxidation numbers, that we will learn how to use these oxidation numbers for the redox reactions next week also. So, what happened with this guy? In this case, oxygen works all the time with -2. There is one exception, and that exception is the peroxides, but we will learn that later. But for most of the cases, it works with -2. Yes? So here you have a simple system equation. X minus 2 is equal to the external charge of the whole anion. It's -1, so X will be +1. You see it? So in this case, the chlorine is working with the smallest oxidation number, 1. And that's the reason why, in that case, we use the terminology hypo and ite. Yes, hypo, the prefix, ite, the suffix, and in this case, chlorine is working with the lowest oxidation state. Let me go for the second one. ClO2 -1. In this case, X will be the oxidation number of chlorine minus 2 times -2, because we have 2 oxygens, and each oxygen is working with -2, and that is equal to -1. So X will be +3. So in this case, we call it chlorite, because it corresponds to the second oxidation number, the smallest. Then we do the same with the ClO3 -1. X plus 3 times -2 is equal -1, so X will be +5. And as you can see there, it's working with the third oxidation number from the lowest to the highest positive number, and that corresponds to the suffix ate, chlorate. And finally, we have ClO4 -1. X plus 4 times -2 is equal to -1, so X is equal to +7. So in that case, we have the highest oxidation number in that case, and that belongs to the top one. So this type of nomenclature happens for all the halogens except the fluorine. Chlorine, bromine, and iodine. And the reason is that in all the cases where you have those no methyls bonded to oxygen, oxygen is more electronegative one, so they work with a positive balance in that case, not fluorine. So that's the reason of this nomenclature. Then after, we have the numerical prefixes for hydrates and binary covalent compounds. In this case, we have the denomination mono, di, tri, tetra, penta, hexa, hepta, depending on how many you have. So remember, the hydrates are just molecular formulas that can be just crystallized with water. We call it water of crystallization. And you have problems about crystallization water hydration in your homework. So that happens with many salts. So you can have many salts like hydrated. Yes, for example, you can have, I will say, like potassium nitrate. It can be dihydrated. So that means that per 1 molecular formula of potassium nitrite, you have 2 molecular formulas of water, of crystallization in between. And in this case, you identify that as the dihydrate. Yes, di is the prefix and the word hydrate in this case. Also, you use that for binary covalent compounds like the oxides. Like nitrogen pentoxide, for example, means that you have 2 nitrogens and 5 oxygens in that case. So let's call the following compounds. In this case, take a look. These 2 is coming from the oxidation number of iron. So it means that, remember, we have iron 2 and iron 3. Yes? So we have iron 2 in that case, and the other polyatomic anion is the perchlorate. Yes? ClO4 negative 1 perchlorate. So we have iron 2 perchlorate in that case. In this case, we have sodium sulfite. The case of sodium is simple. Sodium is here on the periodic table. It works with +1. And the sulfite is one of those polyatomic anions that you need to learn. The sulfite is SO3 negative 2. If you combine that with the cation, which is sodium, these 2 will go here, and these 2 will go here, but sodium is +1. So here, you place 1, not 2, and you don't show that. So in that case, you will have Na2SO3 in this case. And finally, here we have an hydroxide. Hydroxides are compounds which are characterized by a hydroxyl group. They are very common bases. And all of them contains this, and this is the hydroxyl group. Hydroxyl anion. So all the hydroxides contains the hydroxyl anion. And all of them can be called hydroxides. So all of them are hydroxides of a methyl. Yes? So in this case, we have barium. Barium works only with +2 because it belongs to the group 2A. Yes, so barium is here. So it works with +2 and the OH is -1. So you exchange that and you have barium hydroxide. But look, this barium hydroxide is a hydrate. And how many waters of hydration you have in there? 8. So you have an octahydrate. So in this case, you have barium hydroxide octahydrate in this case to indicate the water of hydration. In this other case, you have a molecular a polyatomic anion here, and in this case, this is called acetate. And because you have 2, you call it barium, which is the cation. This 2 is coming from barium, diacetate. In this case, you have sodium sulfide. But this is wrong. Please, you need to correct this. Sodium sulfide has the formula this, and it's wrong because what we have here is not sodium sulfide. What we have there is a sulfite, not a sulfide. Yes? So in this case, please fix that because sodium sulfide, it is not polyatomic in the case of the anion. Remember, a sulfide contains sulfur -2. So sodium sulfide must be Na2S. So the corresponding formula for sodium sulfide is that one, not wrongly what you have on the slide. Please correct that. Yes? In the third case, you have iron 3 sulfate. This 3 is coming from iron. This 2 is coming from the charge of the sulfate, -2. And in this case, you have cesium carbonate. Cesium has +1. It belongs here to the group number 1. And carbonate is polyatomic and has -2. So very simple. You exchange that. You name them. So now let's name the binary acids. So we have 2 different types of acids, the binary ones and the ones that we call the oxoacids. In the binary ones, it's really simple. In this case, we have the combination of hydrogen with a non-methyl. And we call them hydro for the hydrogen, then the root, and finally we end that with ic, and finally with the word acid. So it's simple. In the case of the halogens, like for example, HF is hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. The problem arises with the naming of the oxoacids, because the oxoacids depends on the naming of the polyatomic anions. The ones that I show you for the hypochlorite, chloride, chlorate, and perchlorate, those names that you need to remember. So in this case, if you know the naming from the anions, then you will rapidly find the naming for the acid. How to? Well, very simple. In this case, whatever you have in the anion ends on ate, it will be transformed to ic, and whatever you have ite in the suffix, it becomes os. The prefixes hypo and per are retained. So in this case, for example, here we have the perbromate. And the perbromate, if you add one hydrogen here, you have this acid, which is an oxoacid, and it's an oxoacid because it contains hydrogen and no methyl and oxygen. And in that case, it passed from perbromate, 8 is changed by ic, so it's perbromic. And in this case, iodide, ite is changed by os, so it's iodose acid in this case. So here, name the following anions and give the name of the formula acid. So simple: bromide, iodate, cyanide, sulfate, nitrite in this case. And then you use the same naming we saw before to name the acid. In this case, we have the hydrobromic acid. In the second case, we have iodic acid. In the third case, you have, how do you call it? HCN. Hydrocyanic acid. Hydrocyanic acid. In this case, sulfuric acid. And in this case, nitrous acid. Okay? Because the nitric acid is with the NO3 in that case. So finally, with the nomenclature and the naming, a binary covalent compound is typically formed by the combination of two non-methyls, and some of these compounds are very common and have trivial names. For example, this one, instead of calling that as an oxide from hydrogen, we never call it like that way. So you don't find the name hydrogen oxide. The name you have for that is water, and it has been used since all the life. But no, that doesn't happen for most of the other compounds. So the element that is second in name is using the root with the suffix "ide," like an oxide, for example, a hydride, for example. The numerical prefixes indicate the number of atoms of each element present. So let me give you the namings for this. In this case, look, we have carbon disulfide. In this case, carbon and disulfide. We know that in this case, we have carbon, and then we have S2. Carbon disulfide is CS2. In this case, we have phosphorus pentachloride. Yes, we end with the suffix "ide," and then give the name and formula of the compounds whose molecules each consist of 2 nitrogen atoms and 4 oxygen atoms. So in this case, the nitrogen lower group number than oxygen, the compound's formula N2O4, and in this case we call it dinitrogen tetraoxide. I know that some of you fell in one of the questions from the homeworks because you used the common name for one of the oxides of nitrogen instead of call it like dinitrogen monoxide. Yeah, you call it nitrous. So many of you asked me about that problem in one of the questions from the homework. So in this case, we have monosulfur pentafluoride, dichlorine etaoxide, and dinitrogen trioxide. Finally, you have the naming of the hydrocarbons. But you will see the details of this later in Gen Chem 2. I won't go over the details of that. What you should is just learn the most basic names of the most simple hydrocarbons, which are consisting in only carbon and hydrogen bonded by single bonds. These are the alkenes, 1 till 10. This is what you need to know. Nothing else. The remaining ones are going to be learned in Gen Chem 2 and in orgochemistry. So in this case, here we have the most common ones. So we use the prefix meth for 1 carbon, eth for 2 carbons, prop for 3 carbons, but for 4 carbons, pen for 5 carbons, and so far. And we use the denomination N, in this case the suffix, to indicate it's an alkene. So CH4, C2H6, and so far. This is what you need to know. Nothing else about organic chemistry till the moment. Till the moment. Now let's see molecular formulas, and we will start immediately with the calculations then after. So here, the molecular formula just indicates to you the sum of the atomic masses. And in the case of the water molecules, it's just very simple. You go on the periodic table, you find the molar mass of, or the atomic mass of hydrogen. You find that for oxygen here, and then you sum both, and you will have the molar mass of one molecule in this case. In this case, we are using atomic mass units to indicate we're doing the measurement of one molecule, but then after we will see the topic mole. Mole is related to the Avogadro's number that I'm going to teach later. So for the moment, AMU is atomic mass unit, and it corresponds to the units we use for atomic level and molecular level, not moles. In the case of ionic compounds, we refer that as formula mass, yeah, or formula weight also. But it's exactly the same meaning of molecular mass. So I will skip this. It's so simple. Use the periodic table and calculate the molecular formula or the formula weight for tetraphosphorus trisulfide. So in this case, we have 4 phosphorus and 3 sulfur and ammonium nitrate. In the case of the ammonium nitrate, we need first to draw the formula of ammonia. In this case, we have ammonium nitrate. So we have 2 nitrogens, we have 4 hydrogens, and 3 oxygens. So just assume all the things. I know that most of you know that perfectly. I won't go over the details. Now let's see the representation you need to be familiar with, and then we are almost done to start with chapter 3. So in this case, we have water. In this case, we have the molecular formula. Here we have the Lewis dot representation that we will use later to represent a Lewis structure of a molecule. You can use single bonds. Each double electrons here are the sharing of 2 electrons represent the creation of 1 covalent bond represented by a single line. Here, so we have structural formulas. In this case, we add the shape of that molecule. That molecule of water is bent, and that's what you see here. And finally, you add like the real volume, which is occupied by the whole atoms involved in that molecule. And in that case, you will see the van der Waals ready space field topic. So we can see the molecule this way, this way, this way, and this way. And till this moment, we will consider the molecule this way, and perhaps this way. Later, we'll consider this way and this way during this class. Finally, remember, we can have what we call mixtures. And in the case of mixtures, we can have homogeneous mixtures and heterogeneous mixtures. So in the heterogeneous mixtures, you have 1 or more visible boundaries, and that is the case of sand. So you have different compounds. In that case, they are not connected to each other, and you can see chemical boundaries. In this case, you can see the difference of the things inside. So if you take sand and you put that sand on your hand, you can see different type of particles, crystals in there. But you cannot see that on a solution. So in a solution, you don't see boundaries. You don't see any separation. So in a solution, like for example, sugar dissolved in water or salt, common salt dissolved in water, you don't see any separation. In those cases, you have a homogeneous mixture. So sand or any suspension represents a heterogeneous mixture, and a solution represents a homogeneous mixture. So most of the reactions we're going to see in this class are based on homogeneous solutions. And well, I will skip this, and because these are different techniques on how to do the separations. Just please read this. I'm not going to ask you that on the exam at all. And these are important techniques that you will use later in your lab, in the Gen Chem, but perhaps in the Orgo lab later. Okay, so I won't go over the details on how to do the physical separation of molecules. So I will skip this, and let's go for chapter 3 calculations. So the first part, before we start with the stoichiometry calculations, is the concept of mole. Look, mole, okay, mole is really important term in organic and in inorganic chemistry, of course in general chemistry. And the topic mole comes from a guy who studied how many entities does 13 grams of a substance has. And that guy was a physicist, chemist from Italy. His name is Amedeo Avogadro. And Avogadro was the first to determine how many particles or boundaries you have in 13 grams of carbon. In this case, 12 grams of carbon. So look, the mole is the amount of a substance that contains the same number of entities as there are in exactly 12 grams of carbon-12. And the molar mass of carbon is 12. So the term entities refers to atoms, ions, molecules, formula units, electrons, Dr. Lopez, you, the books, whatever. So 1 mole of Simon is, the Avogadro's number of Simon in that case, okay? So it's really important that entities can be atoms, molecules, things, whatever. And 1 mole of any entity represents 6,022 times 10 to the 23rd entities in that case, and that is the magic number of Avogadro. Avogadro's number, that's a number you need to memorize, 6,022 times 10 to the 23rd. So 1 mole of atoms contains 6,022 times 10 to the 23rd atoms. 1 mole of molecules contains 6,022 times 10 to the 23rd molecules. We abbreviate that as N, italics, upper. And here we have a representation of 1 mole of different substances. So here we have 1 mole, here we have 1 mole, here we have 1 mole of different entities like sand, like salt, like sugar, like a methyl, like water, or like popcorn in this case. Yes, the seeds for popcorn. Now let's see the term molar mass and how that relates to a mole. The molar mass is what 1 mole weighs. Yes? So the molar mass of a molecule represents what 1 mole of that molecule weighs. Yes? So in this case, a substance is the mass per, the molar mass represents the mass of a substance per mole of entities. For monoatomic elements, the molar mass is the same as the atomic mass in grams per mole. The atomic mass is simply read from the periodic table. So remember that till now we consider everything as AMU. And AMU represents units for molecules or for atoms in that case, but we can extrapolate that to grams. So for example, we can say that the atomic mass of hydrogen is 1.008 AMU or 1.008 grams per mole. When we refer to grams, it's grams per mole. And remember, 1 mole is 6,022 times 10 to the 23rd of those atoms. For molecular elements and compounds, the formula is needed to determine, of course, the molar mass. And then you can find the ratios in between the two. In this case, it's just multiplying 2 times the molar atomic mass of oxygen, so it's 32 grams per mole. You can determine exactly the same for SO2, and you can find many ways to. Okay, so here is just a relationship in between the atoms, in this case, the moles, the Avogadro's number units, the AMU units instead. So it's really simple. In this case, you can convert moles to grams just using the molar mass. You can convert the mass into moles also using the molar mass. You can combine also the Avogadro's number with the moles. So having the moles, you can transform that into entities using the Avogadro's number, or you can have the entities and then transform that into moles. It's different ways too. But you don't need to memorize this at all. What you need to is just apply the logic and common sense to do your convection factor. Yes, the units you need to cancel and the ratios you have in between those units to solve the conversion factors. So when you have an amount of any element in moles, you can use the molar mass to calculate the mass, or you can use the Avogadro's number to transform that into atoms or molecules. So let's apply that to a simple problem. In this case, we have silver, and silver is used in Urali, table word, but not in longer in US coins. How many grams of silver are in this quantity of moles? So it's really simple in that case. Remember, to do a conversion factor, you need to start from what you have. And you need to imagine, well, where do I need to go? In this case, you start with the moles you have. In this case, the moles we have is 0.0342. Moles of what? Moles of silver. Yes? And the question is asking us how many grams. So, simple conversion factor. We say, well, we know that 1 mole of silver weighs how much? The molar mass of silver from the periodic table is 107.87. Yes? 107.87 grams of silver. So in this case, we cancel the moles, and immediately we can calculate the grams of silver. Really simple, this case. So in this case, it's equal to 3.69 in this case. Now let's go for the following problem, gallium. In this case, we have gallium. It's a key element for solar panels and whatever. How many gallium atoms are in this quantity of moles of gallium? So in this case, we have the concept of moles and atoms. So in this case, we need to apply the Avogadro's number. To do that, we start with the quantity we have and we go for atoms. In this case, we know that 1 mole of gallium atoms, how many atoms contains? 6,022 times 10 to the 23 atoms. So in this case, we have 2.85 times 10 to the negative 3 moles of gallium times 1 mole of gallium contains 6,022 times 10 to the 23rd atoms. So in this case, we cancel the moles, and immediately we can get the atoms of gallium. So in this case, this is the number, 172 times 10 to the 21 gallium atoms in this case. Then we can combine both. We can combine the grams, the moles, and the atoms. So in this case, iron is the main component of steel. And whatever, it is also essential in the body how many iron atoms are in this quantity of grams. So in this case, what you need to do is just transform the grams into moles and the moles into atoms using the conversions from the Avogadro's number and the molar mass of iron. So in this case, we start with what we have, in this case, 95.8 grams of iron. And we transform the grams into moles using the molar mass from the periodic table. If you check there, the atomic mass from iron is 55.85. So 55.85 dividing grams of iron is what 1 mole of iron. We cancel the grams and now we have mole of iron. But the problem is not asking us about moles. The problem is asking us about atoms. And we know that 1 mole of iron atoms contains the Avogadro's number. So 1 mole of iron atoms contains the Avogadro's number of atoms. 6022 times 10 to the 23rd iron atoms. And here we obtain atoms of iron in that case. So in this case is 104 times 10 to the 24 atoms of iron. So here you can see that using the Avogadro's number now, we can transform that quantity in moles that before we were able to transform into grams and into molecules. We can also transform that using the chemical formula also in moles of the elements or moles of the compounds also. So let's consider the following problem. Nitrogen dioxide is a component of urban smoke. How many molecules are in this quantity of nitrogen dioxide? So in this case, we are not talking about atoms. We are talking about molecules. So here we are introducing a new concept. Because we have 8.92 grams of nitrogen dioxide. And nitrogen dioxide is a molecule. Yes? So in this case, nitrogen dioxide, and the problem is asking us how many molecules are in that case. So in this case, we transform these into moles using the molar mass. The molar mass is easy to calculate here. So oxygen is 16 times 2 is 32, plus the molar mass of nitrogen is 14. So it's 32 plus 14, 6 is 46. So 46 grams of NO2 is 1 mole of NO2 molecules. So we cancel the grams and we have mole of molecules. But we know, based on the Avogadro's number, that 1 mole of molecules contains 6022 times 10 to the 23 molecules. So in this case, 1 mole of NO2 molecules contains 6022 times 10 to the 23 molecules. And finally, we have molecules of NO2 in our calculation. So the first is, well, be careful, because on the exam, you will be in front of certain problems that won't tell you the formula. It will tell you the name, yes? And if you don't know the naming correctly, you will fail on the calculation. Suppose that instead of that, you place a wrong formula, so you will fail on the calculation. So be careful about that. So now, let's complicate the things a little bit more. Ammonium carbonate, a white solid that decomposes on warming, is a component of baking powder. How many formula units are in this quantity of ammonium carbonate? And then after, how many oxygen atoms are in this sample? So in this case, remember, in this case, we are talking about formula units because this is an ionic compound. In this case, the first we need to is draw the correct formula for ammonium carbonate. So remember, ammonium is a polyatomic cation, and ammonium is NH4 plus, and carbonate is CO3 negative 2. So ammonium carbonate is NH4 parenthesis 2 CO3. So the first is this, okay, molecular formula. And then the problem is asking us how many formula units are in 41.6 grams of ammonium carbonate. So in this case, what we need to is just start with what we have and transform that into formula units. Remember, formula units will be the equivalency of molecules in the case of ionic compounds. So in this case, we have 41.6 grams of ammonium carbonate and we need to cancel the grams, so we use the molar mass of ammonium carbonate. And that is what contains 1 mole of ammonium carbonate. So in that way, we will cancel grams with grams of ammonium carbonate. Now we have moles. But the problem is asking us in part 1, how many formula units? And again, this is an ionic compound, and formula units will be similar to molecules. Yes, similar, not the same, but similar too. So if you continue that, I will continue here. You say, well, 1 mole of ammonium carbonate contains how many formula units? Magic number, 6,022 times 10 to the 23rd. So 6,022 times 10 to the 23rd formula units of ammonium carbonate. So you cancel the moles here, and now you have the formula units. So in that way, you can solve part A. Then after, the problem is asking us about how many oxygen atoms are in this sample. So if we want to continue, we can continue this calculation because we know that 1 formula unit of ammonium carbonate contains how many atoms of oxygen? Based on the molecular formula. How many? 3. So it's very simple. In this case, if you want to continue, you say, well, 1 formula unit of ammonium carbonate contains 3 atoms of oxygen. You cancel the formula units and you will finish with the atoms of oxygen in that case. Yes? So in that way you can solve part A and part B. Very easy. So in the slides you have the quantities, okay? But this is the way you need to do it. In the slides you will see the problem in parts. I just solved the problem in just 1 big conversion factor. So as you can see, it's common sense and just using the units, using the ratios of the conversions. Now let's calculate the mass percent from a chemical formula. That's very simple. In this case, the mass percent of any element is just the quantity of that element over the molecular formula times 100. It's very simple. So in this case, let's do that using glucose. Glucose is a really important molecule for us because it gives us the power, the energy we need to work, the energy we need to wake up, okay? And glucose have that following formula, C6H12O6. You will see that many times in organic chemistry and in biochemistry for those taking biochemistry later. So what is the mass percent of each element in glucose? So simple. In this case, how to do that? The first what you need to do is what? Can anyone tell me? The first what you need to do is what? Calculate what? The molar mass of glucose. Yes? And from the molar mass of glucose, during your calculation, you will determine also the molar mass of the elements present there. So simple. So in this case, take a look. We have 6 carbons for glucose, and every carbon weighs 1201. Yes? So for carbon, we have 6 times 1201. For hydrogen, we have 12 times the molar mass of hydrogen, which is 1.008. Of course, grams per mole. For oxygen, we have 6 times 16, which is the molar mass of oxygen. So with that in hand, you will have the quantities in grams for each one of those elements. You sum all the resultant, and you will have the molar mass. And then to calculate the percentage of each of the elements, just divide the grams of each element over the molar mass times 100. So in this case, if you do that, it's really simple. In that way, you can calculate the grams of carbon, you can calculate the grams of hydrogen, you can calculate the grams of oxygen. So you have the molar mass, and then you divide the grams of each over the molar mass times 100, and you have the percentage of each one of them. Really simple. Finally, we have the mass percentage, and then this is the last slide. The mass percent and the mass of an element can also be used to calculate the mass of a particular element. So in this case, you divide just the mass of that element in 1 mole of compound over the mass times the mass of the compound, and you will have the mass of the element. So I will stop the class here, guys. Guys, be careful with the hurricane, okay? So I don't know if that will affect us. I pray for not. But just in case, be safe, okay? So see you next week, hopefully. I look good. Nicer, huh?
Yeah.
Oh, yeah.
Clean.
I need it.
It wasn't too bad before.
Yeah.
How can we know, like, all the polyatomic ions that we need to memorize? Is there a list?